This video we will learn how to easily predict the products of different alkene reactions. We will learn the mechanisms and the reagents for each reaction. So let's go ahead and get started. The first reaction that we will learn is halogenation. Halogenation is a reaction where the reagent is Br2 or Cl2. And for all of this reaction, our starting material will be an alkene, which means a C double bond C. So all of these reactions, we must start with an alkene, a double bond, and then we will use specific reagents to make specific products. For each reaction, I'm giving you a brief overview of how to easily and simply predict the product. So here, for Br2 or Cl2, what you will have to do is you will have to turn your double bond into a single bond, and you will add 2 bromines or chlorines depending on what your reagent is, 1 on each carbon from the double bond. And I also wrote that the stereochemistry will be trans. Trans means one will be wedged and another will be dashed. So let's go ahead and look at this example. We have a double bond, so that means this is an alkene reaction, and our reagent is Cl2. So according to my product prediction, what we have to do is we have to turn our double bond into single bond, which I have done here. Then I will add 2 chlorines because my reagent here is Cl2, so I'm going to add 2 chlorines on the 2 carbons that had the double bond. So these 2 carbons had the double bond, and I'm going to give each one a chlorine. And I also said that stereochemistry is trans. So if I want to show stereochemistry, if your teacher is asking you to show the stereochemistry, you will have to make one wedge and another will be dashed. And there will be another molecule where this chlorine could be dashed and this one will be wedged, and it will depend on your college whether you have to show both of them or not. Let's go ahead and look at the mechanism. So for the mechanism, we have the double bond attacking the bromine, and the bromine attacks the double bond back, and one of the bromine leaves. So this mechanism is with Br2, but it will be the same with Cl2. In the mechanism, it's really important to know that you make this intermediate, which basically looks like a triangle. It's called bromonium ion intermediate. We have bromine with a positive charge, and we have this triangle looking intermediate. What happens next is that the other bromine is going to go ahead and attack the carbon, the more substituted carbon from my bromonium ion intermediate. It will attack this carbon, and then the bond between the carbon and bromine will break, giving electrons to the bromine, and that's how we get 2 bromines on the 2 carbons that had the double bond. Note that the way that this bromine attacks is an SN2, and remember that for SN2, when we attack, the stereochemistry of the product is inverted. So that's why this carbon will change stereochemistry. I did not show stereochemistry here, but I'm explaining why the product is trans. So because it's an SN2 reaction, this carbon will change its stereochemistry, and this one, the stereochemistry will be the same. So we have, that's why one of them will be wedged and another will be dashed. We have different stereochemistries. Now let's go ahead and do the next reaction. And let me change my color to a darker blue. So the next reaction is, again, we start with alkene. Just a reminder, all of the reactions we're learning today, they have to start with a double bond in order for them to occur. So we have an alkene, and we also have Br2 or Cl2, but this time we have it with water. So I wrote for the product, all you have to do is turn double bond into single, and you will have to attach OH to the most substituted carbon from where the double bond was, and Br or Cl to the least substituted carbon from the double bond. And again, our product is trans. So let's go ahead and do this problem. We start with an alkene, and we see Cl2 with water. So let's say that this is an example. I turn my double bond into single bond. That's done. Then I'm going to attach OH to the most substituted carbon from the double bond. My double bond used to be here. These are the two carbons that had it. The more substituted carbon is here because it's attached to 3 carbons, so this is a tertiary carbon. And so I'm going to attach OH here. This carbon is attached to only 2 carbons, so it's less substituted. And my Cl will go here. Again, stereochemistry is trans, so if you want to show stereochemistry, you can show your OH wedged, and you can show your Cl dashed. And since OH is wedged here, my methyl group will be dashed. Or you could show another product where Cl would be wedged and OH would be a dash. And then this methyl group will be a wedge. Again, it depends on what your professor is looking for. Maybe they don't even want you to show the stereochemistry, or maybe they want to show all of the possible products. So we will have these 2 products, which are enantiomers. And in the previous one, I just showed 1, but it would have 2 also. And here we have, the most important thing to remember is that you turn the double bond into a single bond, and you attach OH to the most substituted carbon from where your double bond was, and Cl or Br, depending on your reagent, to the least substituted carbon from where the double bond was, and these 2 attachments will be trans. Now let's go ahead and look at the mechanism again. I put the mechanisms for the reactions that I thought were important to see the mechanism from. So here again, the mechanism is pretty much the same as last time. We attack the bromine attacks the double bond back, and the second bromine leaves. We make bromonium ion, or as I say, the triangle. And then instead of bromine attacking like in the last example, because we have water and water has 2 lone pairs of electrons, it's the oxygen that will attack the most substituted carbon, and the bond between this carbon and bromine will break, giving bromine a pair of electrons. Again, this is an SN2 reaction, and that's why the stereochemistry on this carbon will change, and this one will remain the same. That's why they will be trans. In the last step, our OH2 plus. So what I am attaching, let me just change this positive. Let me just make it more beautiful looking. So I attached my water. I attached the oxygen is the atom that bonded to the carbon. So I show this bond. The oxygen still has 2 hydrogens on it. So I show 2 hydrogens. And it will be positively charged if you calculate the formal charge, because it's connected to 3 bonds now. And so I have to do an extra step where I basically deprotonate. I can take my Br minus, and I can take off this hydrogen to just leave me with an OH. And so I will have OH and Br, and again stereochemistry will be trans. So OH could be wedged, Br could be dashed, and vice versa. And the reason it's trans is because of this step where water attacks and in SN2 fashion changes the stereochemistry of this carbon, and this carbon has this the stereochemistry it started out with, even though I'm not showing you stereochemistry here, but I'm just telling you why it happens. The next one, so all of these are basically different kinds of a very similar reaction, halogenation. So first we just learned regular halogenation with Br2 or Cl2. Then we'll learn Br2 or Cl2 with water. And the last one we will learn, well, it's not the last one for alkene, but the next one we're learning is Br2 or Cl with alcohol. R represents any hydrocarbon chain. So this R could be CH3OH, CH3CH2OH, and so on and so forth. I wrote here, all you need to do is you will have to turn double bond into single, and you will have to attach OR to the most substituted carbon from the double bond. and you will have to attach bromine or chlorine, depending on your reagent, to the least substituted carbon from where the double bond was. Again, our stereochemistry is trans. So let's go ahead and do this example. I turn my double bond into a single bond. Then these are the two carbons that had my double bond. This one is connected to 3 carbons. This one is connected to only 1 carbon. So this is tertiary and this is primary. Tertiary is more substituted. So I put OR. What is OR here? I add oxygen. And what is my R group here? It's CH3. So it's OCH3. Now for this carbon, I'm going to attach a bromine, and again my stereochemistry will be trans. One will be wedged, one will be dashed. Let's go ahead and do the next one. Next one, I guess this is number 4, and this is oxymercuration. Oxymercuration, again, our reactant is always alkene for these reactions. We need to remember, because sometimes students get confused, how do I know which reaction it is? You always look at the starting material. If your starting material is a C double bond C, an alkene, and if you have a reagent that's one of these reagents that we're learning, it must be one of these reactions. So alkene, my reagent is HgOAc2 with water, and the second part is NaBH4. And here I wrote what happens. You will have to turn double bond into single bond. Notice a pattern. We always do this, almost always do that. I will not say always. There will be a reaction where we do not. But for the most part, we turn double bond into single bond. And we will add OH to the most substituted carbon from the double bond and H to the other carbon, which is not as important. The most important, of course, is the OH. In this reaction, there is no rearrangement, which is important because there is another reaction that gives us OH and the most substituted carbon, alkene with H3O plus or alkene with water and acid. But that reaction has rearrangements that we have to worry about. If we do not want rearrangements, we can simply do this reaction. And if you're not aware about rearrangements or what it is, you can watch my video on rearrangements to get more familiar with it. Okay, without further ado, and I'm sorry for my handwriting, let's go ahead and do this reaction. We see that we're starting with alkene and we're doing oxymercuration, where our reagent is HgOAc2 water and NaBH4. So even though the reagent is very long and looks complex, all we do is we turn double bond into single bond, done. And then we add OH to the most substituted carbon from the double bond. My double bond was here. This carbon is attached to 1 carbon. This carbon is attached to 3 carbons. So this carbon is more substituted. It's actually tertiary. So I'm going to go ahead and give OH here. I could also put a hydrogen on this carbon, but it's not really necessary since there are already hydrogens there. We don't have to really show it. Again, it depends on the professor and it depends on the type of problem. But here's my product. OH on the most substituted carbon from the double bond, not on the most substituted carbon in a molecule, just OH on the most substituted carbon from the 2 carbons that had the double bond. Now we will quickly do the mechanism. We see an alkene, HgOAc2. The intermediate in this reaction again will be, I will call it a triangle. That is not the scientific name, but I'm going to call it a triangle. Mercury ion basically. And the way it's very similar to the intermediate in our halogenation reaction where we had bromonium ion. And so all we have to do is we will attack water, because water is together with the mercury reagent. Water will attack the most substituted carbon. The bond between this carbon and mercury will break and water will attach. In the next step, water will get deprotonated. So you have, and let me make it look better, you will have OH on the more substituted carbon and mercury with 1 acetyl group on the less substituted carbon. And then in the last step, we use NaBH4, and it replaces our HgOAc with a hydrogen. Now, if your teacher wants to be tricky, they could say we will use NaBd4, deuterium, which is an isotope of hydrogen. Then what happens is, instead of hydrogen next to OH, you will get deuterium. Another way your teacher could be tricky is, instead of using water here, he could use D2O, where instead of hydrogen you have deuterium. So then instead of getting OH here, you would get OD. Again, it depends from one college to another. Everyone is very different. The reagents might vary slightly also, because different professors might show you different reagents, but these are the most basic ones. Our next reaction, let's see, this is not actually 6, this is number 5, is alkene with peroxy acid. So this, it could be CH3COOOH, very, very notable, 3 oxygens. RCOOH, where R could be any group, such as this methyl group, or the most famous one is Mcpba. Mcpba. If you see Mcpba, it's peroxy acid. What do we do when we see this? We will turn double bond into single, just like before, and then we will connect the 2 carbons from the double bond to the oxygen, making what I call a triangle with an oxygen, but that's an epoxide. So for example, I have this, and honestly most professors use Mcpba, but some professors just write CH3COOH, peroxy acid, CF3COOH, so it does depend on your college. But what I do is I turn my double bond into single, then I identify the 2 carbons that had the double bond right here, and I simply connect them to an oxygen like this, and therefore I made the epoxide. Now I wrote here the stereochemistry is concerted, which means that if I start with a cis double bond, when I make an epoxide, these 2 methyl groups that were on the same side, they will be still on the same side. So for example, they will be washed. If I start with a trans epoxide, it will still be trans. And so we just learned a reaction of how to make an epoxide. Once you make an epoxide, there are more reactions that could happen with your epoxide. So once you make an epoxide, you could stop there, or your professor could give you more reactions with an epoxide. There are 2 types of epoxide reactions. The first type is epoxide reacting with an acid, and the second type is epoxide reacting with a base. When an epoxide, so in order for you to do these reactions, the first thing you will have to do is identify, do I have an acid or do I have a base? Remember that an acid will have an extra hydrogen like HCl, HCN, something that can give a hydrogen, and a base will have a negative charge usually like NaOH, and we will NaOCH3, which means you have Na plus, OCH3 minus, or they will just give you CN minus. So you just have to be aware of identifying your acids and bases. Now, in an acid, this is what I wrote. You will get rid of the epoxide and put OH on the least substituted carbon from where the epoxide was, and your nucleophile, whatever your nucleophile is that you get from acid, on the most substituted carbon from epoxide. So what happens here, and I am also showing the mechanism, is, for example, if you have your epoxide with HCN, the first thing that happens is that oxygen takes the hydrogen. The way I usually teach my students is I say that you can imagine epoxide being a birthday girl, and she's having guests, and HCN is a very generous guest and brings her a present in the form of a hydrogen. So the epoxide is very happy, and she allows the Cn minus to go ahead and attack it from the most substituted carbon. Again, because you're going through this triangular intermediate, and you're attacking in SN2 fashion, you will result in a trans product. So epoxide that react with acid or base also give trans products. So here we have Cn minus attacking the most substituted carbon. The bond between carbon and oxygen breaks to give me OH. And so I have OH and I have Cn. Cn went to the most substituted carbon. Remember, look at this carbon. It's connected to 2 carbons, so it's secondary. This carbon is only connected to 1, so it's primary. So we went to the most substituted carbon, to the secondary one. Cn attached to the most substituted carbon. OH attached to the least substituted carbon. Stereochemistry will be trans. It's going to be either wedge Cn-OH or a dash Cn wedged OH as my products. Now let's go ahead and look at the epoxide with base. So in basic conditions, you also get rid of epoxide, but you will put OH on the most substituted carbon from epoxide, and base will go to the least substituted carbon. In the mechanism, again, you can think of epoxide being the birthday girl. Base does not give any presence to it, it just attacks right away. So the birthday girl gets upset and tells the base to go ahead and go to the least substituted carbon. So the base attacks from the least substituted carbon, and it attaches to the least substituted carbon from the epoxide, and then you will have O minus. And a lot of times this attack is followed by some sort of acidic condition, so that oxygen can get protonated to become OH. So the end result will be OH on the most substituted carbon and base on the least substituted carbon. And we will go ahead and we will take a look at some of the examples of what kind of bases could attack an epoxide that are unusual. So one example is a Grignard reagent. If you see Mcbr, you know you have a Grignard. The carbon that's attached to Mcbr basically has a negative charge, and Mcbr is flowing in the air, so you can think of it like that. And what will happen is that this carbon is going to attack the least substituted carbon, push these electrons up, so you will get your Grignard reagent, in this case your benzene ring on the least substituted carbon. That's the carbon that attacked. So the carbon that attacked will attach to the least substituted carbon from the epoxide, and you will get O minus on the other carbon, which could be protonated later on through acidic conditions. Here, let's just take a look quickly. Let me erase my arrows for now. I have CH3O minus. I'm going to say it has a negative charge. It's a base. Sometimes your teachers could say NaOCH3, for example. You have to recognize this is a spectator ion, Na+, this is minus, so it's still a base. It's the same thing. And basically, again, the base is going to go to the least substituted carbon. This carbon is less substituted than this from the epoxide, and break this bond, and so you will get O on the most substituted carbon and OCH3 on the least substituted carbon. You could use some sort of acid afterwards to protonate your oxygen to make an alcohol. And I'm not showing stereochemistry here, but you still have to remember that stereochemistry is trans. Every time you go through what I call the triangular intermediate, but in this case an epoxide, every time you will break your epoxide, your stereochemistry of the products will be trans, because it attacks in an SN2 fashion. Now, another kind of base that we can think of is lithium aluminum hydride, and you can think of it as H minus. And I wrote here that you will get rid of epoxide and just put OH in the most substituted carbon. Hydrogen will go on the least substituted carbon from where the epoxide was, but we don't really care much about it. So if we have this epoxide, we don't really have to show the mechanism, but if we do, it's H minus that attacks like this. and we will get at the end OH on the most substitute carbon, H on the least substitute carbon, but we don't even have to show this H. Let's continue with our epoxide. Another one that we could, another kind of base. So all the bases I'm showing you here, they're unusual, not something a student would recognize right away. So this is some of the cases that I'm showing you. In case you will see it, you will know how to predict the product. So the third one is organocuprate, and these are not the only bases that could react with epoxide, by the way. There's so many different bases that can react with epoxide, just like acids. So many different acids that could react with an epoxide as well. So in organocuprate, this is my R group. Organocuprate reagent looks like this. You have 2R, CuCN, Li2. You can think basically of what's inside the parentheses as R minus, and attacking again the least substituted carbon from the epoxide because it's base, and bringing the electrons to the oxygen. So you will have, in this case, OH on the most substituted carbon, and then this was my R group, CH2, CH3, and that will be on the least substituted carbon from the double bond. In the next lesson, I will continue and do more alkene reactions. I hope you enjoyed this one, and I look forward to seeing you in more of my organic chemistry videos. Thank you.